Saxon Advanced Mathematics. We forgot to cross off 69. We're on lesson 70, week 19 of the year. We're in our 6th week since the winter break. Look how much work we've already covered. Man, you guys are working really hard, and I've had this conversation with several of you over the past week or so. One of the sad things about math is that it's a very private, introverted, individual course of study, right? There's no way to share it with other people. We don't read our poems aloud. We don't even have a science fair. There's no band concert, right? There's no way to share what we're learning except with each other. So I am celebrating with you all of this work that you've been doing. You might not be studying with anyone else who's following the same path as you. So let me say, I see how hard you're working. I am so impressed. It takes a huge amount of discipline and focus to do what you're doing, and I'm really impressed by you. So, huzzah. All right, we're gonna talk a little bit more about statistical measures. We have talked most recently about this thing called a normal curve, a normal distribution, and that is when there are enough samples of something and it behaves in such a way that when you graph out all of the results, you get this really, and mine's not perfect, you get this really beautiful bell-shaped curve, right? This is called a normal distribution. And we can make this cool graph by putting right in the middle, pretend it's perfect, right in the middle is the mean, right? That's the average score of anyone who took the test. Then we can calculate this thing called a standard deviation. And when we move one standard deviation out from the mean on either side, we capture 68% of the results, right? So we can say 68% of the students taking this test, let's just say, they scored within one standard deviation of the mean. Then we can calculate 2 standard deviations, going out another, whatever that amount is from here to here, we go out the same amount. Again, my picture's not perfect, pretend it is. When we go 2 standard deviations in either way, we capture 95% of the scores. And if we go a third standard deviation out from the center, we capture, what is it, 99%? Yes. In real life, these numbers are not as exact. They are decimalized, but we're not going to worry about that. All right, so if you take, say, a standardized test, then you know what the standard deviations are, then you can compare and see how many standard deviations out from the center you are. Now, I don't know about you, but for most people, that's not very meaningful. That's not very interesting way to look at it. What we want to know is what percentage of students did we do better than, right? And we call that the percentile score. And what that measures is how many people did we do better than in the case of a test, okay? So let's look at 2 individual people. John gives them great names. This person's name is Charlie Mack. Oh man, I want to be named Charlie Mack. That's a great name. Charlie Mack's score was 150. Well, because, I didn't tell you this, because the mean is 150, then when we color in his score, we know that because the mean is right in the middle, he is the 50th percentile, okay? That means 50% of the students scored lower than he did. We tend to measure the lower result. In this case, it's really easy to see, oh yeah, there's 50% are higher than him too, right? He's right smack dab in the middle because his score just happened to be equal to the mean. But what about our other friend? And John gives her, I think they're both girls, I'm not sure, an equally splendid name. Her name is Zolly. Wow. I hope someday to meet someone named Zolly. She scored 171. Now that's a really good score. And we know it's better than 50%, right? Because 50% is 170. But, so we're just gonna guess she's like somewhere up here maybe, is her 71%, or 171 is her actual score. We wanna know, what percentile is she? Okay, we don't really care about standard deviations. That's not meaningful to the ordinary human being. We want to know what percentile. Did her score hit? All right. The classic examples for talking about this are scores on standardized test, and the other one is, I don't know if you guys have ever had experience with this other than as the baby, but you know how babies go to a lot of checkups at their pediatricians, babies and toddlers, to make sure they're growing on track? What the doctors do is they weigh and measure the baby's height each time they come in, and then they track that on a normal curve, comparing it to all the other babies that have been born in many years, and they come up with the baby's percentile height and weight. So if you're a parent of a young child, you're really familiar with this percentile thing because it's a big, you want to make sure that your baby's tracking in a normal percentile, right? If their weight is 90%, 90%, and then the next time you go in, it's a 10%. If they're at 10%, then you know something's gone wrong, right? So the percentile is a big deal. What we're going to learn how to do in this lesson is calculate this percentile so that we can compare individual scores to a normal distribution and come up with a meaningful way of comparing it. So, how do we calculate a percentile? It's 2 steps. First, we calculate what's known as a z-score. I know that sounds mysterious, but don't worry. The way that we calculate it is using this formula. Greek letter. I think it's called mu. Let me see if I can find out quickly. No, I'll worry about that later. It's a Greek letter. I'll tell you what it stands for in just a second. And we divide it by the standard deviation. Okay, so X equals the individual score. And in Zolly's case, it was a 171, right? This fancy business is the mean, and then we divide the difference of those two by the standard deviation. And we learned how to calculate those, but I think in these, John's just going to give us that value. Okay, so that's the first step. Then, once we simplify this, that's the z-score. I'm going to write equals z, just so that's clear. Then, okay, then once we have the z-score calculated, right there, then we look it up on a table that's in the book, and I'll show you in just a minute. But it's as simple as just looking it up in the book. All right, so we're going to use this process to do a couple examples. 1, 2, 3. Yes, there are 3 examples in this lesson. Ready? So that was my opening preamble. It was kind of long this time, but I wanted you to understand what the heck we're doing and why we're doing it. Okay, example 76.1. The mean weight of the babies born in a metropolitan hospital for 7 years was 6.8 pounds. Okay, this is the symbol for the mean, and in this case, they just told us it was 6.8 pounds. with a standard deviation of 0.8. If the distribution of the weights were approximately normal, yay, that means we get to use our curve in this table and everything's fine. So that's just good news. What percent of the babies weighed less than, we're supposed to find the percent of babies weighing less than 6.4 pounds, okay? So we're gonna use that as our individual score. So this will be equal to X, all right? And then we'll interpret this when we get to the end, don't worry about that. Okay, so our calculation, again, Z equals X minus mu over omega. I always forget the names of the Greek letters, but this is the mean and this is the standard deviation. I remember their mathematical purposes. In this case, it will be 6.4 minus 6.8 divided by 0.8. Make sense? And then that simplifies to, let's see, this is negative 0.4 over 0.8. And so that equals negative, this is 1/2, right? So we know it's 0.5. That is our Z-score, okay? The minus sign matters, so it's minus 0.5. Now, here comes the book. On page 442 in my copy of the text, for lesson 70, we're in here. Down here is what's called a standard normal table. That's what I'm talking about here. Our Z-score is minus 0.5, 0.5. So what we do is we're looking for a Z-score that, here's the whole numbers, 0, and then 0.5 we'll find up here. Now, notice there's negatives and pluses. Notice there's negative zeros and positive zeros. That's weird. We don't usually think of 0 as being a positive or negative, but we've got numbers with decimals in them. So like our example is negative 0.5. So we want the negative 0 with the 0.5. That's a different number than if you had positive 0.5, right? So that makes sense. Negative 0.5 is 0.3085. So I'm gonna write that down. Okay, the percentile for negative 0.5, I'm gonna put the 0 in just to help make it clear, is 0.3085. That means 30.85% of the babies in this sample weigh .4 or less. Okay? This is the answer to our problem. If your baby was born and weighed 6.4 pounds, you would be at just under the 31st percentile, right? 30.85 babies weigh less than that. Okay, so that shows how we calculate the Z-score and then use that with the table. This was step 1 and this was step 2. You just look at the table and read your result. Step 2 is, it's not necessarily easy to figure out that chart, but there's no calculation to it. Let's do another one. Sometimes John will ask the questions in a more roundabout way, and we have to do a little bit of common sense thinking that make these problems kind of interesting. Okay, let's do 70.2. Ready? In this same hospital, what percentage of the babies weighed more than 7.2 pounds? Okay, so we have the same mean. It was 6.4. No, 6.8. And our standard deviation is still 0.8. See, John's not making us calculate that. He's just giving it to us. But we do have the formulas. We know how to calculate that if we have the right data. But now, we don't have to. Okay, my marker lid's flying all over. And this time, wait, I did this wrong. This is the mean. The actual individual score we're looking at is 7.2. We want babies. We want the percent of babies that are more than 7.2, okay? One thing about these problems that isn't really clear is whether we're including 7.2 or whether we want greater than 7.2. It's a little murky and confusing. My advice to you is don't overthink it in these problems. Just choose 7.2 and don't worry about, does that include 7.2 or is that 7.2000001? John does not make that really clear in these calculations, so we're not going to worry about it. Okay. Oh, I'm doing the wrong problem. I'm doing 7.3 instead of 7.2. Let's just roll with 7.3. That's confusing. Okay, so what we've got here is 7.2. Okay, so we want to do, first we want to calculate our z-score. It's the mean. It's the individual score minus the mean divided by the standard deviation. This is 0.4 positive over, oh, I'm sorry, I put the decimal in the wrong place, 0.8. So that is positive 0.5, right? Last time we did negative 0.5. So now we want to look that up on the table. I kind of like doing this one next because it points out how these zeros work. Now our z-score we're trying to look up is 0.5. It's positive 0.5. So now we use the positive 0 and we go to the 0.5 and it's 0.6915. Okay, so the percentile of babies that equal 7.2 pounds is what did I say? 0.6915. But remember, this percentile measures the percentage of babies that are less than. It always measures to the less than side. But our question is, what about the babies that are greater than 7.2? So that's this area. I'm going to polka dot it. Messily. Okay, we're interested in this. So how do we find this percentile? Well, we just take 100%. And I'm going to switch this into a percent from a decimal, 6915. We just subtract, right? Because the whole curve is 100, and we know that 69.15 of the babies are less than that because the table measures to the smaller side, not to the larger side. So if we want the larger piece of it, we just have to calculate. This would be 5803. I'm borrowing in my head. So that tells us that 30.85% of the babies born in this mythical hospital are 7.2 pounds and greater. All right, that's this side. The 6.1915, which is 69%, that relates to this side. So we just subtract from 100. Okay? I hear you saying, okay, sounds good. All right, now let's go back and do 70.2. I kind of like doing those two together, though. That actually made a certain amount of sense. 70.2 is also from this same hospital. For example, 70.1, so they're saying use all the same data. What percentage of the babies weighed between 6 pounds and 7 pounds. Okay, this is going to require 2 calculations, right? Because what we have to do is we have to figure out, here, let me draw a little picture. You know, if there's any reason to draw a picture, I'm gonna draw it. If you know anything about the Seattle area, you know that Mount Rainier is a huge old dormant volcano that's south of the city. It's got a really nice bell curve shape. So whenever I draw these out, I always think of Mount Rainier. Okay, so what we're saying is that the mean is 6.8, right? We want to know, 6.0 and 7.0. I didn't draw those lines perfectly proportional. It looks like this one's 8.8 and this one's 0.2, so it would be more like here, wouldn't it? I drew it too far. But what we're asked to do is find the percentage of babies within here. No, within here. No, I was right before. This is where the 7 is. I changed it, right? So we're looking for these babies between 6 and 7. Okay, so what we'll do is we'll calculate the percentage of babies at 6.0 and at 7.0, and then we'll figure out what to do with the answers when we get there. Okay, so our formula is, right? And our mean is 6.8, and our standard deviation is 0.8. We're starting with this as our individual score, so it's 6.0 minus 6.8 divided by 0.8. Oh, I see what I was doing. I was setting up a little table, but I changed it, all right? So there's our actual score minus the mean divided by the standard deviation. Here, we'll have the actual score minus the mean divided by the standard deviation. All right, I was using those as titles, but I'm just gonna make the calculations. All right, this would be negative 0.8 over 0.8, which would equal -1 and then 0.0, because our table has decimals. All right, so we'll look that up in a minute. This is all step 1 where we're calculating our z-scores, right? This is our z-score. It's a negative. All right, and then this one would be 0.2 over 0.8, which is 1/4, which is gonna be 0.25, positive. And that is our other z-score. They get separate puffy clouds of knowledge. They're going to live together. All right, so now we go to our table and we find the percentiles for both of these. So the first one is -1.0. Grab my book. -1.0, 0.1587. Is the percentile for this value. And then this calculation, we have a z-score of 0.25 positive, 0.25. Now, we go, okay, it would be 0, 2, but there's no 0.25. How are we gonna find 0.25 if the chart doesn't go that far? What we're gonna do is we're gonna take 0.2 and 0.3 and we're gonna average them. Oh, yes, we are. So we're going to take those two scores and find the average and use that as the percentile for our score, which is 0.25. Could we round that 0.25? Yeah, but you can see we would round up we would round up and we would lose a lot of subtlety. So dividing these in half, taking the average of this, because we want 0.25 is not that big of a deal. We can do it. Okay, so we're gonna take 5793 and 8849. 8849 no, I went to the wrong number. 5793 and 6179. These are the two numbers we're going to average, and that will give us the value for 0.25, which would be right in between those. Okay, here I go. We take 0.5793, that's the z-score of 0.2, and then we take 0.6179, that's the z-score for 0.3. We add them together, and we divide by 2. And so that gives us a percentile for this weight of the babies of 0.5986. I did that by hand when I was looking at this lesson to review, so I'm not going to do it again, but there are our two scores. Now I want to draw a picture to show you what we've got so far. Oh no, I'll just use this picture again. What we found is that babies who are born at a weight of 6.0 represent 15.87 percentile, right? All the babies less than 6%. If you weigh 6 pounds, you're at the 15th, almost the 16th percentile. That's how many babies are back here, right? All right, if you were born at 7 pounds, you represent the 59.86th percentile, right? And that covers all the way from 0 up to the 7 pound weight. So it's all of this. Okay. Our question asks us to find just this zone. Okay. The ones between 6 and 7. So to calculate that, we take the 59.86%. I'm going to do it on the next page. We take the 59.86%, which represents the 7.0 pounders, and then we take the 15.87%, and that represents the 6 pounders, and we subtract to get that space in between, and that is 43.99% that fall between 6 and 7 pounds. That's our answer. And we'll go look at the picture one more time. So this region here, this red only, that is the difference. Oh, I'm using my purple marker. Oops. I'm just gonna have to cover it up. That's how we find the region between 6 and 7, is we find the percentile for 6 and the percentile for 7, and then we subtract. All right? This one I think is the hardest of the 3 problems, so I'm glad I did them out of order because I think it worked better that way. The z-scores are here in your book, as I said, on page 442. That's called the standard normal table. It takes your z-scores and converts them into percentages. I'm sure you can find these online and calculate them. I would rather, don't just Google like what percentile z-score equals 2.5, right? If you find the table online and look it up yourself, that's fine, but don't just Google for the specific result. I want you to get comfortable using the table because it is a little awkward. It's different than any tables we've used, and honestly, we don't use that many tables. So, All right, that is lesson 70. I hope you enjoy this little diversion into statistics land. I hope you enjoy drawing pictures of Mount Rainier / the normal curve. And I will see you for lesson 71. We get to draw more pictures. I'm very excited. Okay, bye.